Section: Introduction. In this section, we explore the intriguing phenomenon of abrupt learning in transformers, where the model's performance remains stagnant at a suboptimal level for a while before quickly improving to an optimal solution. This behavior is part of a broader concept known as emergence, where model capabilities develop unexpectedly as we increase parameters, training data, or training steps. Understanding these sharp changes in learning is essential for grasping how transformers acquire their advanced skills. While there has been progress in understanding these abrupt dynamics for specific tasks, a comprehensive explanation of model evolution during loss plateaus is still lacking. Many existing studies rely on specific assumptions that limit their applicability. Our aim is to uncover universal traits and mechanisms that define these training dynamics across various tasks. We seek to identify common patterns in the model's behavior and internal representations during the plateau phase and to determine what changes lead to improved performance. We also want to know if there is hidden progress occurring during the loss plateau. To systematically investigate these questions, we focus on training small, shallow transformers on simple algorithmic tasks. This smaller model size allows for clearer analysis and interpretation of internal mechanisms, avoiding the complexities found in larger models. The algorithmic tasks we examine, such as moving window sum and multi-digit addition, have clear optimal solutions, enabling us to measure the model's progress accurately. Our contributions include identifying implicit biases during the early plateau phase, where the model learns partial solutions while being biased towards simpler patterns. We also examine the role of attention map learning in overcoming performance plateaus. Specifically, we find that during the initial plateau, the model often predicts easier tokens correctly while struggling with more complex parts of the task. We observe a strong repetition bias in outputs, where the model tends to produce repetitive tokens, which decreases as performance improves. Additionally, we note that this repetition bias is linked to representation collapse, where hidden representations for different tokens become very similar. As the model's performance improves, this similarity decreases, indicating a diversification of internal representations. We discover that the learning of optimal attention patterns can begin during the loss plateau, and by adjusting the attention map during training, we can influence the duration of the plateau and the severity of issues like repetition bias. Finally, we validate that these phenomena are not exclusive to small transformers but also occur in the early pre-training phases of larger models like Pythia and Olmo, suggesting they are fundamental characteristics of transformer training dynamics. We present our main findings using the moving window sum task while also validating them across various other algorithmic tasks. Section Summary. In this section, we explore the phenomenon of abrupt learning in transformers, where models experience prolonged performance plateaus before rapidly achieving optimal solutions. We identify key characteristics during these plateaus, such as the emergence of partial solutions, repetition bias in outputs, and representation collapse, and demonstrate that these behaviors are also present in larger language models, highlighting their significance in understanding transformer training dynamics. Section: Data. In this section, we describe the moving window sum (MWS) task, which requires us to calculate the sliding window sum of a sequence of numbers, using a window size of 2 and taking the result modulo a number. Page our input sequence consists of numbers followed by a separator token, and we aim to produce an output sequence based on this input. For our experiments, we set the length of the sequence to 16, the modulo value to 17, and the input numbers are uniformly chosen from 1 to 16, with the separator being 17. Our vocabulary includes the numbers from 0 to 17. For the model architecture, we utilize a simple one-layer, one-head transformer with causal masking and linear attention, which effectively solves the MWS task with perfect accuracy. The output of the transformer for a sequence of tokens is generated through a series of operations, including embedding the tokens, applying attention, and passing through a multi-layer perceptron. We ensure that all linear transformations include a bias term and apply layer normalization before certain operations. During sequence generation, we use greedy decoding to select the output token based on the highest logit from the vocabulary. We chose linear attention to prevent issues with vanishing gradients that can arise from softmax attention. In terms of training, we focus on minimizing the cross-entropy loss for predicting the next token in the sequence. We evaluate accuracy based on the output tokens and use the atom optimizer with a fixed learning rate. Our training process involves drawing new batches of training samples at each step, leading to similar training and test losses. We observe a distinct abrupt learning curve during training, where the loss remains stagnant for a while before rapidly decreasing to an optimal value, accompanied by a quick rise in accuracy. We also analyze the attention map at various training stages. After the sudden drop in loss, we notice a clear and interpretable attention pattern, where each output token attends only to the relevant input tokens. We introduce an attention progress measure, APM, to track how the attention map evolves towards this optimal pattern during training. This measure shows a steady increase throughout training, even during the loss plateau, indicating progress before the loss drop. Section Summary. In this section, we describe the moving window sum, MWS, task, where we compute the sliding window sum of a sequence using a simple one-layer transformer model that achieves perfect accuracy. We also analyze the training dynamics, noting a characteristic abrupt learning curve and the evolution of the attention map towards an optimal pattern that reflects the relevant input tokens for each output. Section. Implicit biases in the early phase of training. In this section, we characterize several important signs of implicit biases during the early phase of transformer training. These patterns consistently appear alongside a plateau in loss, indicating that the model may be stuck in a less effective state. We observe that during this loss plateau, the model often learns a partial solution to the task. This means it can accurately predict some output tokens, usually the simpler ones, while struggling with the more complex parts. For example, in the MWS task, the model quickly learns to predict the first output token correctly, as it simply mirrors the first input token. However, the overall loss remains high, and the accuracy for subsequent tokens is low. This ability to tackle easier components early on is seen across various algorithmic tasks. Additionally, we notice a strong repetition bias in the model's outputs during the initial training phase. This bias refers to the model's tendency to produce repeated tokens, like X, 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 and so on. We can measure this repetition by counting how often an output token matches the next one. We find that this repetition frequency increases rapidly in the early training phase, reaching about 0.8 after approximately 50 steps, indicating an implicit bias from gradient-based training. We also investigate the relationship between hidden representations at different output positions, finding a significant phenomenon of representation collapse. In this phase, these representations become nearly identical, except for the first output position, which is correctly predicted. We measure the cosine similarity between hidden representations at different positions and find that this similarity increases rapidly, averaging around 0.95 for all positions except the first. This representation collapse does not occur at initialization and only appears after a few training steps, contrasting with the rank collapse seen in deep softmax attention transformers at initialization. We note that while the loss dynamics are abrupt, the measures of attention progress, repetitions, and representation collapse are not. Even when the loss barely decreases, attention progress improves, along with a reduction in repetition frequency and representation collapse. Our training time interventions show that learning the attention map is crucial in influencing the loss plateau, repetitions, and representation collapse. Finally, we verify whether the attention layer contributes to representation collapse during the early training phase. We analyze the cosine similarity of the residual stream for output tokens before and after the attention layer. We find that in the early phase, the cosine similarity in the post-attention representations quickly approaches 1.0, unlike the pre-attention representations. Additionally, the norm of the post-attention stream grows rapidly, while the norm of the pre-attention stream remains nearly constant. Thus, we conclude that representation collapse occurs after the attention layer during the early phase of training. Section Summary. In this section, we characterize implicit biases in the early phase of transformer training, noting that models often get stuck in a loss plateau while learning partial solutions, exhibiting strong repetition bias and representation collapse. We find that these phenomena, including increased cosine similarity between hidden representations, occur after the attention layer and are influenced by the learning of the attention map, despite the abrupt loss dynamics. Section: Biasing the attention map. In this section, we explore the impact of the attention map on training. We adjust our training process by starting at different points and biasing the attention map towards or away from the optimal configuration. This helps us determine if issues like repetitions, representation collapse, and loss plateau are reduced or increased. Specifically, we begin at a certain training step and multiply the attention map values for output tokens, except for the first position, by a constant greater than 0. If this constant is greater than 1, we bias the model towards the optimal attention map. If it is between 0 and 1, we bias it away. Our findings show that when we bias towards the optimal map, we see lower average cosine similarity between hidden states, fewer repetitions, and faster convergence. Conversely, when we bias away from the optimal map, the model experiences longer representation collapse and converges more slowly, with high repetition rates persisting. For instance, starting with a large bias, 10 times, results in a peak cosine similarity of about 0.6, significantly lower than the 0.95 achieved without bias. Similar trends are observed with different starting points in training. Next, we test training with the optimal attention map by fixing certain parameters to their final values from a previous training run. We then retrain the remaining layers from random initialization. We initialize the attention layer parameters in two ways, either just the key and query weights or all weights including value and output. In both cases, retraining the subsequent layers takes much less time than training the entire model, with no significant issues like representation collapse or loss plateau. We also find that including the output and value weights slightly improves learning speed and increases average cosine similarity. However, fixing the MLP or embeddings does not significantly alter the training dynamics, as we still encounter loss plateaus and repetition bias. This suggests that the attention map is more critical than the MLP or embeddings in influencing training outcomes. Finally, we investigate the repetition bias observed in transformer models during early training, which coincides with loss plateaus. We find that this bias persists even with minimal repetition in the training data. Additionally, we demonstrate that learning simple, repetitive sequences is easier for transformers, which may explain their tendency towards repetitions in the early training phase. Section Summary. In this section, we investigate the impact of biasing the attention map during training, finding that increasing attention values towards the optimal map reduces representation collapse and accelerates convergence, while decreasing them leads to prolonged learning difficulties. Additionally, we demonstrate that initializing the attention layer with optimal values significantly improves training dynamics, whereas fixing MLP or embeddings does not yield similar benefits, highlighting the critical role of the attention map in mitigating repetition bias and loss plateaus. Section: Beyond repetitions in consecutive tokens. In this section, we explore the issue of repetition bias in language models. One possible reason for this bias is that the training data may contain repetitions, which the model learns to amplify during early training. To examine this, we focus on a task with minimal repetitions in the training data, specifically the prefix sum task. In this task, the outputs are defined as the sum of the input values up to a certain point, taken modulo a number. We ensure that there are no consecutive repetitions in the outputs. When we train a transformer on this task, we do not see a significant increase in repetition frequency, unlike in other tasks. However, we still notice that a few tokens appear repeatedly in the model's output, though not in a contiguous manner. To better understand repetitions, we introduce a measure based on entropy, which quantifies the diversity of tokens in the output sequence. Lower entropy indicates that a few tokens dominate the output, while higher entropy suggests a more uniform distribution. We find that the model's output entropy drops quickly during early training, indicating some level of repetition bias. Additionally, we observe that representation collapse occurs early on, with the average similarity between representations increasing significantly. Next, we investigate what happens when the training data contains many repetitions. We analyze a simple task where the output is always the same token. In this case, the loss curve does not plateau, suggesting that these repetitive sequences are easier for the model to learn. We find that just one gradient step can significantly improve the model's performance. We also define a metric to measure how often the model outputs the same token across all positions, which shows a rapid increase in early training, indicating a tendency to repeat the first token. Finally, we confirm that repetition bias and representation collapse are not limited to small models but also occur in larger language models during their early pre-training stages. We analyze early checkpoints of open-source models and find strong evidence of representation collapse, with average cosine similarity values increasing sharply in the initial training steps. This pattern is consistent across different models and sampling methods, demonstrating that these phenomena are prevalent beyond simple tasks. Section Summary. In this section, we investigate the repetition bias in models during training, finding that even in tasks with low repetitions, such as the prefix sum task, the model exhibits a form of repetition bias early on, indicated by low output entropy and high cosine similarity among representations. We also demonstrate that repetitive sequences are easier for the model to learn, leading to significant representation collapse in larger language models during their early pre-training phases, confirming that these phenomena extend beyond simple tasks. Section: Related work. In this section, we review previous research on abrupt learning, which has been explored in various contexts. Some studies focused on parity tasks using different neural network architectures, while others examined abrupt learning in Markov chain tasks with transformers. We found that training a BERT model for matrix completion resulted in abrupt learning, and there are connections between abrupt learning and grammar data setups related to graphs. Recent works have also investigated abrupt learning and in-context learning, providing both theoretical and empirical insights. Our goal is to uncover a unifying explanation for these observations in an algorithmic framework that accommodates multiple tasks with multi-token outputs, without imposing strict limitations on our model or training conditions. Additionally, we note that recent research on grokking, where models show sudden generalization after a period of memorizing training data, has been approached from various angles, including circuit design, representation learning, and the dynamics of feature learning. However, grokking is tied to fixed datasets, while our focus on abrupt learning pertains to online training, meaning there is no memorization of training data involved. Theoretical explanations for plateaus and sudden drops in loss during transformer training have been linked to saddle-to-saddle dynamics, but these require specific assumptions about attention mechanisms and initialization scales. Other studies have applied concepts from statistical physics to analyze initial loss plateaus in a two-layer teacher-student neural network setup, revealing that symmetry and weight vectors during early training stages can lead to loss reductions. We also highlight research on stage-wise training dynamics in transformers, which estimates the local learning coefficient to explain the loss landscape's degeneracy. The relationship between simplicity bias and transformer learning dynamics has been explored, showing that neural networks tend to learn simpler data moments earlier in training. While repetition in language model outputs is a well-documented issue, most studies focus on pre-trained models rather than the early training phase. Some researchers noted that early outputs might include word repetitions, but this was not their primary concern. Rank collapse, a related issue for deep softmax transformers at initialization, differs from our representation collapse, as we utilize shallow transformers and linear attention, with our representation collapse occurring shortly after training begins. We identify repetition bias and representation collapse as significant features of the early implicit biases in transformer training, closely linked to the observed loss plateau. Understanding why this degeneracy occurs early in training is a crucial area for future research. Moreover, We demonstrated that the slow learning rate of attention maps contributes to prolonged plateaus, raising questions about why this rate is slow for algorithmic tasks and how it relates to the task's complexity.